slide presentation. And I get a presenter console. Very nice. Really nice. PDF PC. Free open source. Download. All right. Welcome. Hello. I am Paulo Raposo. This is my clever, excellent undergraduate student, Jordan Brown. And we're here to tell you a little bit about this recent project that we've been working on. It's about a new OGC standard. You may have heard of Discrete Global Grid Systems. So these are coordinate systems and geometric tessellations of the Earth that are meant for various things. Much of the idea is to implement these in lieu of Latin long as a coordinate system. So we'll have a look at them. So Jordan and I recently actually coded one up because we couldn't find any existing code to do it. And we've made that code open source, so in case you ever have reason to use the fancy hierarchical tessellation of the spherical globe, you can use it. Anyways, so what's DGGS? Discrete Global Grid System. So it's tessellation, meaning it's a coverage of the spherical or ellipsoidal surface of Earth, in this case, or some planetary body. And there's no gaps or overlaps in the tiles, right? And it covers everything. So there are lots of ways you can tile the sphere, if you will. Sphere, ellipsoid, doesn't matter. For simplicity, I'll say sphere. Okay. There's lots of ways that you can actually geometrically chop up the sphere. And those different tessellations have different benefits. Some of them are equal area, for example, as in each little tessera has the same area as every other, right? Some of them are not. Some of them are sort of intuitively simpler. Some of them are a little bit more mathematically complex, right? Here's 4 examples of different ways that you could chop up the Earth into these sort of discrete areas. And there's another example. So usually these things are based on one of the Platonic solids. So these are 5 polyhedra that Plato, back in ancient Greece, determined had certain nice geometric and algebraic properties, right? And these properties become useful in an application such as this. So in every case here, these are regular polyhedra, which means that the faces, they're usually triangles, some of them are pentagons or square, but the faces are the same size and shape as every other face, right? So you have a relative kind of equivalence all the way around the shape. And you can see as you start adding sides, right? That's a 4-gon, that's a 6-gon, that's an 8-gon, 10, can't remember right now. So, but as you start adding sides, it becomes closer and closer to a sphere, right? It becomes a closer approximation of a ball. So usually what people do to build a DGGS, because there are several, is they take one of these, they circumscribe it in the sphere, so you put this shape in the ball of Earth, and you project out the side edges, and presto, you have a tessellation, right, of the spherical surface, and then you recursively subdivide the faces, right? So for example, on the left, you see an icosahedron, right, which is made up of triangular faces. You would put that inside the globe, right? And then you would subdivide each triangular face, so you can see the 2 gray ones, subdivide them into 4 more triangles. And you can do that ad infinitum. So as you keep doing that, and as you keep projecting the new triangles back up to the surface of the ball, back up to the surface of the globe, you have a finer and finer mesh that you've tessellated the spherical Earth into, right? And these things function as many things. They can function as some form of sampling grid, same way pixels do in 3D raster, right? Or they can function as some data indexing schema, which is often the idea behind DGGS, is that you would save, think of it as a database schema, if you will, that you would save geospatial data in this format. Why would you do that? Because this sort of recursive thing might remind you of quad trees, because conceptually it's essentially the same thing, right? So a quad tree takes some space of values. In this case, it's a bunch of points on the Earth, right? Takes some space of values and then recursively chops it down into 4 or smaller. So when you start looking at how computers index memory, that speeds things up a lot. So some of you, I'm sure, are very familiar with that. Others, it's new. But it's basically a way of building a global or spherical quad tree, right, essentially. So the Open Geospatial Consortium, right, our friends who decide a lot of the standards that we use, a little while ago started thinking that they should make this a standard, and they have now. But in 2016, they put out this press release open for public comment. You know, what do you folks think? Should we make this some form of data standard, much like the geo package that they've got now? So this is also they call this one an abstract standard. So it's a standard data format. It's not a specific file format, but it's a schema format. And it has just recently become a new specification as of last year, right? So there's a relatively small group of people, scholars at least in the world, who are working on DGGS, but it's been happening since the 80s. And as you can imagine, if you recursively subdivide every polygon, you have an exponential growth in polygons. So a lot of the early research was limited by computers that couldn't really handle very deep levels of these tessellations. But there's a lot of research on this going now. It's a new OGC standard, and you're going to hear about it more and more, I think. Right. So we implemented specifically, and Jordan's going to come up and talk about this because I had him write some Python code along with me. We implemented a certain one invented by this guy Dutton, Jeffrey Dutton, 1989 is when he first presented quaternary triangular mesh, which is maybe not the easiest thing to rattle off your tongue, but quaternary in the sense that each face breaks down into 4 more faces, right? And it starts with an octahedron. It's one of those platonic solids. Right? You orient the octahedron to the globe so that one of those corners is at 0 latitude, 0 longitude. Another corner is at the North Pole, another corner is at the South Pole. And effectively, by projecting those faces, you've got 8 primary beginning divisions of the globe. And as you continue to subdivide them, you get finer and finer. Question? Yeah.
Real quick question. So, like, if people are familiar with how globes are made,
sure.
The strips
The
are
gores.
basically latitude and longitude. So there's slender at the top,
Yep.
slender at the bottom, fat at the equator.
Yep.
So there's kind of a misprojection of how they're lined up. Is this to fix that?
In part.
Okay, so now I'm
One
following
of-
what you're saying.
yeah.
You're trying to give it more of a congruency rather than the.
One of the arguments that I don't completely agree is theoretically sound is that the DGGS are trying to get around projection problems.
Okay.
Right. So we'll talk a little bit more about that, though. So yeah, I know what you mean with the lenticular globe gores.
Right, gores.
Right, exactly. Yeah. Jordan, take it away. Can you? Sure. Or you can too.
Okay, so what we have here is kind of our base map for the mesh. So we created these using a Python script, which we'll go over in a little bit more detail in a minute. But the format, instead of using shape files for these, which we started out with, we ended up settling on using the GeoJSON format. And because of that, we did a lot of work in Q, which was really nice for handling our GeoJSON. But this is the base map for our mesh. We've got the octahedral shape here, and essentially it's flat here, but we'll map to the globe.
Yeah, so that's the octahedron unfolded and projected in a flat carré projection. And as we subdivide it,
so here we can start to see the first few subdivisions. One of the major issues with it is before it's mapped onto the globe, while it's in 2D here, we get this kind of warping, non-triangular shape the closer we get to the poles. And as we continue to subdivide, we can see the singularity, the warping here getting smaller and smaller, and more of our triangle creation near the center of the map. One interesting thing here, you'll notice the curvature, how the triangles kind of begin to curve along the meridians of the Earth at this point. And this was actually something we were kind of concerned about when we were creating the files at first, because before we had mapped it onto a globe, we were getting these odd, kind of right here, we were getting these odd, jagged shapes that we weren't sure if they were going to map correctly to a globe. But upon actually putting it on the globe, everything meshes pretty well. Here at the South Pole, actually this point and this point, we had to map on separate ends, but they are both the South Pole. And because of that, we can see this really kind of weird warping along the polar regions. But, yeah. As you see, as our resolution increases and we get more and more triangles up here, the warping itself also starts to become less and less significant. Okay, so here's our GitHub repo, where we're hosting the code for the actual creation script for our mesh. Right now, the only thing we have available is the actual shell script that has to be run to create the GeoJSON files for the mesh. But we're working on getting up a repo that will have an actual globe that these scripts can be, that this mesh can be mapped on and play with. Okay, so pretty much everything we used for this work was open source. The only two major libraries that we used were GDAL and InVector, and InVector was a library that helped us deal a lot with the curvature and kind of some of the geodetic calculations for this. I think there's a picture to illustrate it up here in a little bit. But one of the issues with the curvature and the reason we had to use InVector is that we could not map these flat lines onto a globe. If we didn't have curvature, we'd end up overshooting points. Okay, so here's the basic shell interface for our script. The current script that we showed you is pretty simple. You run the script, there's two inputs, an output directory, and the number of levels of the number of subdivisions you want. So each time we subdivide each face by 4, and we can do that pretty much to as much memory as your computer has. There's not really a limit on how deep and how fine the resolution on this mesh can go. So just here's a little picture of our script running. As you see, it only takes about 30 or so seconds to run to level 7. By level 11, you're looking at relatively large GeoJSON files and about an hour's worth of running time and about a 40 gigabyte file. Okay, so the way we mapped this out originally is we created our base map here. You can see the 8 original facets, and we dealt with, as I mentioned earlier, we dealt with the poles by having 2 separate points mapped out for each pole in order to kind of deal with that polar singularity in the 2D plane. And here's kind of the method we use to subdivide each facet from there. Every facet is, based on this, subdivided into 4 triangles.
Okay, great. Yeah, so one of the things we ran into, as Jordan was mentioning, world is round. I don't care what anybody else tells you. And GIS, generally speaking, don't think in round coordinates, almost ever. So GIS work in projected coordinates, generally speaking, right? And often those projected coordinates are just the latitude and longitude angles, but they're still generally, the algorithms are two-dimensional. So that doesn't always work on spherical Earth. So if you're familiar with map projections, they're projecting geometry, at least in the vertex and arc model that we all use in ArcGIS. Projecting geometry and then doing spatial operations on it is an approximation. It's not actually the same thing that's happening on the sphere. Usually the approximation is plenty good enough, but we ran into a case where it wasn't. So we'll get on that. But one of the things, for example, here, as Jordan was saying, to actually map that tessellation in 2D, to create it as something that you can use in a GIS, right? The South Pole had to be represented by 4 different points, right? So it's dealing with that mathematical singularity. Anyhow, the reason we developed this was a side project was this little piece of software that I wanted to write for teaching my own students about the modifiable aerial unit problem, right? So a classic long-standing geography problem where chop up, throw a bunch of data points on a map, chop up that map differently, counties versus census tracts versus whatever, right? As you change those aggregation units, your map, at least the visual appearance of your map, the rhetorical power of your map can change radically, right? And that is the modifiable area unit problem. In statistics, it's related to something called changing your support, which is the sort of aggregation, the aggregation level, if you will, of aggregated data. But the modifiable area unit problem has there's two aspects to it. There's the size of the regions you choose, so bigger and smaller regions cause difference. And then there's the actual shape and location of the regions you choose. So the zoning, scaling, zoning aspects. So we built our QTM in order to build this thing. So this also is all open source technology. So the mesh you're seeing on the Earth right now is what Jordan and I coded up. Basically, it's an algorithmically drawn tessellation, right? And it's being drawn over NASA Whirlwind, which is massively awesome software. It's globe virtualization software. So think Google Earth, but fully open source. Okay? And NASA Whirlwind's it's not an application like Google Earth. You don't download it and use it. It's an API. You download it and put it into whatever app you're using. So this is an app with Java where we can go ahead and I'm just going to use the built-in data, which is a set of population points for the continent of Africa. Right? And what our script is doing, or what our software is doing in the background, a bunch of other scripts that Jordan helped me write, are counting how many points fall into each one of those triangles, right? But doing that repeatedly and recursively. So if I change the level of aggregation, it goes ahead and changes that color scheme based on all those points that are falling in. I can decide to use less colors or more, right? But you can see as I make these changes live, the map reacts, and it kind of tells you different stories, at least in a gut reaction sort of way. And this, in essence, is the modifiable area unit problem. right? The data has not changed. The data in those yellow points has not changed whatsoever. All I'm doing is aggregating it in different ways, right? So I thought a DGGS would be a beautiful way to illustrate it because you could deal with the whole planet this way, right? And if I shift the cells over, this laptop is just a little bit laggy. See if I'm shifting them a little to the west in this case. See points fall in and out of bins, colors change, things that used to look like hotspots don't look like hotspots anymore. That's the modified learning problem, right? And so we built this app to illustrate it, and hence our QTM implementation. So one of the things that we noticed and Jordan touched upon, so these are straight up QGIS exports of the GeoJSON Polygon files. Okay? When a GIS performs math projection, almost universally, it reprojects the vertices. It does not reproject the arc between vertices. Right? So to draw a polygon, we put down a bunch of points, then we connect them with little straight lines. And when you reproject the geometry, those vertices get reprojected and then you string them back up together. Right? But the point is those little lines, exactly where those little lines fall, is not reprojected. Right? That's a linear approximation. Most of the time that's not a problem because those little lines are very little. So the approximation is good enough. Right? As in the inter-vertex distance is small. And so what we usually do is we densify our geometries. We have lots of vertices, even along straight lines, right? So that line curves well enough for whatever our application is. So with the DGGS, we didn't want to densify anything because we already had really big data sets. So instead, we have these triangles that are defined only by 3 points, right? And those 3 points on the surface of the Earth, especially in tessellations that are coarse, like this, right, are really far apart, right? They're many miles apart in the real world. So that straight line, for example, at that level, when projected by a GIS, it's wrong. And that's because all straight lines are wrong. But this is egregiously wrong because of the scale. Because in truth, that line is actually curved, right? And so the next level of detail gets a little closer at it. So as we go finer and finer, we're better and better approximating actual geodesics, as in actual lines defined on the circle. So for example, suppose you did a point and polygon algorithm straight out of QGIS or ArcGIS or any one of them, really, and you were trying to find out which cities are in triangle 60, right? If you did this with a non-densified polygon set, right, you'd get what's on the left and it would be wrong, right? Because that actual left edge of the triangle curves, and you wouldn't get that unless that arc was densified, right? So in our case, we had to deal with this. We had to deal with the fact that two-dimensional point and polygon algorithms wouldn't work, and this is what we needed. So we adapted an old school classic algorithm. Maybe people have heard of it, the point and polygon raycasting algorithm. So take a point, fire a line in any given direction from that point, and if that line intersects with the polygon's edges an odd number of times, it's in the polygon. And if it intersects with the polygon an even number of times, or 0, it's not in the polygon. Right? Simple, classic old schoolers demonstration of it. Right? And we just adapted that to work with geodesics. So instead of these straight line intersection Cartesian stuff, we went over to this n-vector library that handles the geodesic calculation of the curves on the sphere. So same idea, and that's how we figured out which points are in or not a triangle, so that we can subset them and perform analysis like this. That's about it.
So go to that one slide you were just on.
This one?
Yeah. So he, a minute ago, said that the bottom 5 points are the South Pole, right? On each corner. On each corner, you have 2 points on each corner, that's your South Pole.
Yes, this whole line.
So
is
the 3
South
points in
Pole.
the middle are also intersecting the
This
South
is
Pole.
the South Pole, this is the South
So-
Pole, this is, yep.
In theory, if you rotated that 9 degrees, the 3 points in the center, which I assume are on the equator, could also be the poles. Because
Yes.
as you turn it, the geometry is going to stay the same.
I mean, if I turn this.
Right, we could be looking at the poles in the middle
Yes,
rather than on the bottom,
Yes.
at the top.
yes.
So it's following that curve, but also redefining the geometry as you spatially look at it.
You could, you'd have to use a pretty sophisticated reprojection algorithm.
Right, but I mean, I'm
But
saying if
you're-
this was a log model and I
Yeah.
rotated it just
Yes.
like this,
Yeah.
I would get that same image looking down on the poles
Sure.
as I would if I were looking at the equator.
You could, yes.
Okay.
Yeah, same thing could be achieved if you oriented the original octahedron in a different orientation to the globe to start with.
Okay.
Yes, yes.
So Uber just released
H3.
their mesh thing,
Yeah.
right? And I was in an Uber, and the driver actually brought it up, because when I'm doing anything, I wear a geography hat, so I ask stupid geography questions. And he brought it up, and it looked really cool. So how does this relate to, is that related to at all what Uber's doing with their hierarchical mesh hexagon thing?
I haven't read a lot into their stuff, but they are also implementing a discrete global grid system. It's called H3, right? So there's an example of it. Not all discrete global grid systems have perfectly nesting tiles, right? Like the one we did has these triangles that always fit within the coarser level of triangle. But as you can see here, this is mostly hexagonal, right? Interesting quirk, you cannot tessellate the sphere with hexagons. You have to throw in a few pentagons for it to work. So think soccer ball, right? All the white things are hexagons, and then there's these little black ones that are 5-sided, right? So you can do the same thing. You can do the same thing with Earth. People tend to like hexagons. There's lots of reasons to like hexagons, but as you can see, for example, right up there, there's your pentagon hiding, right? So there's various ways of tessellating the Earth, and this one was developed by a fellow, Brodsky was his name, I think, at Uber. And again, that's because they are routing people by routing them from hexagon to hexagon to hexagon. So it's a little bit similar to what 3 words, if people have heard that.
Yeah, they're using basically the same thing.
Right.
For everything.
Right. So what 3 words, 3 by 3 meter blocks of the Earth are each given a unique 3-word combination. Though I still wonder how they do that, because you can't tessellate squares.
Right.
Right. Yeah, you can't get around the round Earth with squares.
And
But the world's flat, we all know
And that projection there doesn't keep everything completely the same unilaterally. It's, you're gonna have octagons, and then you got pentagons, so then you got larger spaces and smaller spaces, and they don't, how do you measure that? You know?
So these are the topics of research in DGGS right now, right? So a lot of people would like to have tessellations where all of the tessera, the individual faces, are of equal area. That's possible, but it's only possible by having some wacky shapes, right? By having relative irregularity of shapes. So often DGGS are a trade-off, right? The one we implemented, the quaternary triangular mesh, is a trade-off. Those triangles are not equal area, but they're almost equal area.
And they're not straight-sided triangles either.
Right. So the first the first few octahedron faces are so on the far right, that's the QTM, the big broad black lines, right? triangle with 3 90-degree corners,
Right.
right? It's a spherical triangle. So it's, I mean, that's not alien to mathematicians, such as this fellow, but it's not something we usually deal with in a projected geometric world.
So there are a few things I was wondering. So with the QTM you have, so I mean, you know, with latitude and longitude, you can define any point near a surface, you know, as a pair of numbers. Is it possible to do that with QTM, and then does that become, is that a pair, or is it a set of like 3 numbers?
Yeah, I didn't touch on it yet, or on this talk, but each face of the triangle, and this is actually something that Jordan implemented in the script, each face in the triangle can be uniquely identified with a string of numbers, right? So what happens is you have your first 8 facets, right? So either 1, 2, 3, 4, 5, 6, 7, 8. And then inside each of them, you start subdividing. And you start doing 0, 1, 2, 3. And you keep going forever, right? And however many levels deep you go, you can address something by saying 6, 0, 1, 1, 2, 1, 3. Right? So immediately you know that you're on level 1, 2, 3, 4, 5, 6 of the tessellation, and that also tells you exactly which triangle, because you always.
So that at that point, you know, you define a region. So the idea is like to define a point. If you keep subdividing the triangles, then in theory you can get a smaller region. Which, I mean, when we talk latitude and longitudes, you know, basically what you do, because like even if it's, you know, to the 5th like decimal degree or whatever, that's still not an exact point. That's some kind of square of, you know, maybe it's 1 foot, maybe it's 10 meters. I'm really not sure.
Yeah, no, you're right. It becomes a matter of precision. That's right.
Okay, that makes sense. That's really interesting. It's kind of like a, you know, it's not even necessarily like a decimal number. It's like a hybrid octal and then base 4.
Exactly.
At some point, I don't remember what level it was, but level 22, I think each subdivision is in the centimeters as far as area. So at that point, you pretty much approximated everything down to points, if you want to look at it like that.
Yeah, which means like at a level 30, you're probably in nanometers.
Right. Oh, that's good to know for scale. The other thing I was wondering, more on a conceptual level, so these triangles, are these flat faces or spherical faces? Like, I'm not sure if.
Another topic of research.
Okay.
So it kind of depends upon how you project the geometry onto the round roll or even weather. So some DGGS specifications just take, as I understand it anyways, they just take a flat facet with these points touching the surface of the globe. And they use that uncurved surface for the facet. But others will project that, right? And you will get, instead of geodesic, right, curved, like a piece of broken eggshell, right? You'll get a geodesic surface. So it kind of depends upon which geodesic surface. Like I said, there's a handful of them. Yeah, if you ever feel like you have a reason to use this, please go ahead and go to the QGIS repo and download it. And it's not a data set in essence that we don't just give you the GeoJSON files because they're freaking huge. So instead we just give you the script that draws them, that will just draw them onto your list algorithmically.
And break. We've got two more talks after this. Yeah, we'll do this with Bert, because your two are gonna kind of blend together, so. See, okay, we'll wrap it up. So I suppose you go out and tessellate all of Raycasting.
Randall?
Yeah. Nah, we're good. We're good though. Thanks for volunteering. I think we got it covered.
So, let me turn the page on.
Work like that?
This looks like what you're doing when we used to tell people about name, using people are using name, check on the line driver. It is apples and oranges. Yeah, but, what you have is an opportunity to improve, help them improve, like you said. Because it's a scrub, that's number 73, whatever it is. Yeah. Well, the optical thing doesn't give you elevation.
No, it doesn't.
But you have it.
And in fact, at work, I work with the North Carolina data, and I've already given that elevation data at 20-foot resolution to the guy working on the CCAP down at NOAA. So he's got that for North Carolina, and I gave him the Virginia stuff too.
They have the coastal area, right?
Yeah, they do all the coastal areas. Yeah.
But while with climate change and ocean rise, all this is hard as heck.
Yeah.
I mean, the analytics part, that's what I do, Well, LiDAR is my thing. Long Cabin was for many years too. So it's like, it's interesting to see how they collide.
Well, back with the first round of North Carolina data, I did that canopy audit statewide.
The whole state. We had LiDAR before anybody else did.
I did it at a 60-foot resolution, and then I went through and did.
Which is 60 feet?
Yeah, it's about a. Yeah. So, and then I did a simulated sea level rise, and looked at what can happen. Actually, I did it for MLCB, with the rest of the show.
What would be lost in terms of build time?
Well, we were looking at actually the vegetative and animal communities.
Oh, yeah.
And then we did the habitat, what percent of the habitat in the state would be lost for each species. And then I looked at the data for the height, and how much, what types of tree heights would be lost as sea level rises at 1, 2, and 3 meter rise. Half meter.
Sure.
It actually was really interesting.
Well, I mean, they have we wasn't in the right. We think it's probably a lot of, but I think that is short. Why is that? It's really not good. And so it has to be so we have a data. We are using those pure Zero the best, one is the next.
They kind of messed up when they did QL4 is the reverse. I think there is some QL3.
There's 0, 1, and 2, and 3.
In Florida, because it's at 1.5 meter.
Yeah, reverse. Yeah. But anyway, so we're using it. We're using it around there. Kind of we have. And I'm curious to see how I missed the first part of
Oh yeah, I would
Did you have free waveforms? No. See, free waveforms will allow you to do kind of structure and biomass and fluid. You know that, right? Right. But I never, I can't even have this data. No. I never have that because it's expensive as hell. But what you do is percentage the physical.
And then they can simulate
Yeah, model. Yeah, so we have multiple. There's a 3 second.
that's the thing, the news, the guy and single
Right, was it like that, regular mode? Yeah. Well, yeah, but that's, oh man, you guys like, I said, the first regular mode, that we got so, you play with the pirates. Yeah, that's what we got, when they were, well, you know, they showed me the video 3 years ago, and they said, this is this, right? It's a problem, so many data.
That's why you have to do the same kind of sampling that I do, because you can go through and through all the masses of data, and you could do.
I agree with them.
Yeah, just do any same thing.
Interesting.
That's the thing. That's part of my full-time job, is to do that. I'm actually sit on the 3 detectives committee.
You are part of the self-help structure.
Yeah, but this is what I do at home. Well, it was a mental itch I wanted to scratch.
Yeah, it is, and it is interesting that we do that.